All of you keep your class test number 2. All of you keep your class test number 2 answer ready. We'll discuss it in last 15 minutes. But your answer to class test number 2 should be ready with you. We will discuss it last 15 minutes. So I think we can start. Am I audible, Nitish? Nitish,
Yes, sir. Audible.
I'm audible, no? So fine. So let me directly go to the discussion of, and because this discussion is slightly heavy, and maybe all of you are facing it for the first time, so I will go little slow at the beginning. In this graph, anything that you think is, first you try to look at the graph, and then if I ask you, what is interesting in the graph? After 2 minutes, look at the graph. Yes, suppose I ask you people, uh, what is interesting in this graph, or what is something that comes to your mind when you look at the graph? Sahil first.
Sir, after a maximum excitation, the excitation goes low, then again goes up.
Excitation?
It fluctuates, sir. Means maximum, then it becomes low, then again goes up.
Okay, that is what you see. ठीक है. Anyone else? You know, this is a very interesting exercise I always talk about. Different person look at the same thing, but differently. The picture is same, but I'm sure individuals will look at it in different manners. साहिल के बाद MTech, Prasad.
Sir, in this graph, it is actually dying after some time.
Correct. But after what time? ग्राफ में क्या देख नजर आ रहा? Tentatively?
Sir, like it is happening in pattern like for the first 5 to 6 seconds.
Agree. But overall.
Overall, sir, decreasing and dying. And in that time,
Agree. But this X scale is up to what?
X scale, sir, it is up to 0.3, I believe, highest.
No. X scale is up to what value?
It look like incomplete, sir.
No. It will incomplete, but the picture is given up to what time?
30 seconds.
30 seconds.
30
30 seconds. Yes, sir.
seconds. And roughly after by the end of 30 seconds, the earthquake is almost gone. Let us agree. Now, what is perhaps, can anybody tell me what I want to tell you about this graph? I mean, I can spend 3 hours on this graph.
In the last 10 seconds, it vibration is.
No. That is fine. I agree. But any question, why nobody is asking me question which is most genuine question?
So initial seconds are dangerous.
Okay,
Maximum.
you all are looking at the graph. Don't you think this sentence itself, the title of the graph also raises some question?
The ground acceleration.
Huh?
It's a ground acceleration instead of ground
Ground?
vibration. Here it is written ground acceleration.
No, what is written is different thing. I'm asking, any query comes to your mind?
There are there two components of a wave, like one is north south and the other is lateral.
This is a good observation. And let me tell you, when you people will work in industry, throughout the world, people are gradually becoming, what should I say? I should not use the word. People are gradually becoming unintelligent. So you have to think differently. So you have to develop that art. You have to see something which others are missing. So Adari Nandana pointed out one of those different things. She is saying this is north-south component. What does it mean? I mean, what do we learn? No, what do we learn? See, you must answer. Otherwise, I mean, it will be very difficult for you even to get a job. These are all common sense question I'm asking. If north-south is written, what does it mean? That there has to be another component which is east-west. And further, vertical. So, two things I don't know whether you have noted or you haven't noted. What we are measuring, first of all, is it a force? Arey bhai,
So it is a ratio of ground acceleration
it is
to.
not a ratio. It is a ratio, but what we are measuring? Listen to my question. This is the problem. I am not saying what is written along y-axis. My question was different. What it is measuring? Is it measuring a force?
No, sir.
No. So please remember, In earthquake, we don't measure force. We measure what is called ground acceleration. Is acceleration a vector or scalar?
Vector.
Vector. So how many direction components it is expected to have? 3. So please remember, earthquake is measured through acceleration and along 3 perpendicular directions. Vertical direction is one of them. Horizontal, again 2 perpendicular direction, north-south and east-west. So this is one of the 3 graphs. Whenever we measure earthquake, we get 3 graphs. This is one of them. This earthquake is measured by an instrument called seismometer. How seismometer works, that is a part of vibration, but I thought that it will be little tougher for you, so I skipped it. But seismometers measure earthquake in 3 directions. The graph they generate is called seismographs. Seismographs. Now, there has to be 3 measurements. One along north-south, another east-west, third one is vertical. All the 3 graphs are important for engineers. Remember that. All the 3 graphs are important for engineers, but vertical graph is, that is the graph along vertical direction is generally considered secondary, whereas graph along east-west and north-south, they are considered primary or more important. ऐसा क्यों? Can anybody explain?
Sir, east, west, north, south represent the 2 axes on which the ground will move, but the vertical will be as up and down of the earth.
Are you answering my question or you are writing a story? Huh? मेरा क्वेश्चन कैसा था? My question was why? Why engineers find it more important, north-south and east-west, compared to vertical? Why? Are they making a mistake? That is my question. Okay, I keep the question open. Every question I am not going to answer right now. So 3 things, 2 things I have already mentioned. One is along the y-axis, we represent acceleration. Either absolute acceleration or acceleration divided by g. If we divide acceleration by g, it is called normalized acceleration. Now, you must have seen that last 1 month or little more than 1 month, whenever the vibration is occurring, we are measuring vibration or we are representing vibration severity through vibration displacement or vibration acceleration. What did you see last 1 month? अरे भाई इधर भी सब चुप. I mean, whenever we discussed a situation of vibration, we measured vibration displacement or we obtained vibration acceleration.
We measure displacement.
Displacement. But here we are measuring acceleration. Why? That is a big question. Okay, that is a big question, but I keep the question not answered right now. That in earthquake, we measure acceleration, not and along y-axis, either we show the acceleration absolutely, that means absolute value, or we show it the normalized value divided by g. Whenever we talk about acceleration, in any case, quite often, rather than saying acceleration is 20 meter per second square, we prefer to put it 1g, 2g, 0.5g, ऐसा क्यों? That is normalized acceleration. The moment I say acceleration is 2g, 3g, that is acceleration in terms of g is called normalized acceleration. ऐसा हम क्यों करते हैं? I'm saying 2g, I could have said it is 9.6 मीटर पर सेकंड स्क्वायर. ऐसा मुझे 2g बताने के क्या मतलब है?
Know the difference from the reference point.
Anyway, that is not the answer. That is not the answer. Now, a very interesting answer is failure of material is generally depends on vibration displacement. But sometimes it depends on vibration acceleration. But most of the time, failure depends on vibration displacement. However, vibration causes another damage. On human being, it causes discomfort. See, if you have been to merry-go-round, I think definitely you have experienced that discomfort. Or bungee jumping. Why that discomfort comes in human being? Or roller coaster drive? It is because of G. So human comfort is also connected with, if suddenly the plane loses its height by 500 meter, you get a discomfort. So that is connected with acceleration. That is not connected with displacement. That is connected with acceleration. So as far as human body discomfort is concerned, it doesn't depend on vibration displacement. It depends on vibration acceleration. So sometimes acceleration becomes a more important parameter. Sometimes displacement become more important parameter. Earthquake, we measure acceleration not because of this, because of something else. And not only earthquake, we measure acceleration. Throughout the world now, it may not be earthquake, it may be a machine vibration under harmonic excitation also. We measure acceleration. We don't measure displacement. But after we measure acceleration, we integrate it. We get velocity, we again integrate it, and then we get the displacement. This is happening because throughout the world now, vibration is measured by a sensor, which is called accelerometer. So this should be discussed in your measurement subject. You are also having a subject called measurement in 6th semester. It should be discussed. Throughout the world now, but 50 years back, vibration used to be measured by other techniques, where direct displacement values were possible. But last 30 years, the technology has switched over to accelerometer, where name of the sensor is accelerometer, which works on the physics of piezoelectric effect or piezoelectric crystals. So these accelerometers are very, very small, very effective, very much accurate, and dynamic range is much bigger. So nowadays, all the vibration measurements are primarily acceleration measurement. However, wherever we want to know the displacement, what we do is we integrate acceleration 2 times. And there are signal processing problems. It's not that easy. Lot of signal processing problems. Again, that should be taught in a subject in mechanical engineering, but that subject is missing. It is called signals and systems or signal processing. And if you tell me, I will say that in mechanical engineering, we are not teaching you some 4-5 important subjects, which is mandatory in the current engineering scenario. One is computational methods, you haven't learned. One is vibration, you are learning perhaps. One is measurement and signal processing. It is very, very important. One is control system. Okay. Anyway, let me come back to this graph. So y-axis is acceleration. That is interesting. North-south component, it is interesting. We learned that there will be another component east-west. There will be another component vertical. But what is the third point to be noted here? Okay, I'll give you again another 15 seconds. Can anybody point out third point in this statement? ग्राफ में हमने ऑलरेडी डिस्कस किया. It is random. It is showing no trend. And more or less after 30 seconds, the acceleration is dying out. That is what we see in this particular graph. But in this sentence, what strikes you? I mean, अपना कॉमन सेंस दिमाग में लगाओ. ये जेई कोचिंग करने गया ना, सब लोग गधे बन गए. जेई कोचिंग हैज किल्ड आवर एजुकेशन. सब लोग गधे बन गए. ये दो सेंटेंस देखने के बाद तुरंत किसी को एक सवाल पूछना था, व्हाट इट शुड बी. अभी भी किसी की दिमाग में नहीं आ रहा. And all of you expect that a company should come and give you a package of more than 10 lakh rupees. क्यों देगा? ये दो लाइन पढ़ने के बाद what should be the first observation, first comment that should come to your mind as a normal human being? If I show it to even a school child, perhaps he or she can also raise that question that I'm expecting. If you look at the title of the graph,
measurement of acceleration is of ground.
तो अर्थक्वेक में तो ग्राउंड ही अर्थक्वेक में क्या है? What is earthquake? Earthquake is ground motion. Earthquake is not wind disturbance.
So, but the device is placed in a building.
Earthquake will occur even if there is no building. Earthquake occurs under the sea also, for information, which causes tsunami. Earthquake के लिए building का कोई जरूरत नहीं है. Building may be there, may not be there. Earthquake has nothing to do with building. If building is there, earthquake will disturb, but earthquake does not require a building to occur.
Sir, the record is only of a particular place, and earthquake is a very big phenomena. So
Go ahead. You are on the right track. Go ahead.
And we don't know at different places what were the acceleration or what were the recordings of that.
Okay. Not exactly what I was expecting, but at least you have started thinking.
There may be maximum acceleration will be different in different places.
It doesn't matter. It will be, definitely it will be. Now, why I am saying it will be? Because I am calling it random. So what is the definition of random? If a signal is random, obviously it will not have same maximum value at the same time. That's why you are calling it random. So earthquake is random. Earthquake signal is always random. And the moment I'm calling it random, obviously I'm trying to say that maximum will occur How much it will occur, I don't know. At what time it will occur, I don't know. So all these parameters will vary from place to place. Fully agree. What you have to now, let me give you the answer, and don't get angry because I am attributing slightly. I'm using some discouraging notes, but it is usual. I am teaching since last 30 years. This batch I am not satisfied. Fine. One, you should have asked me, this is a pretty old earthquake, 1940. Does it mean after 1940 no more earthquake has taken place? Why we are showing you 1940 earthquake? In India, can anybody tell me last 30 years? Listen to my sentences carefully. Last 30 years, there have been two very important earthquakes in India itself. Can you name the places and the year? Roughly. I know you are not born, or you, that is another thing, but you should know the history.
There was an earthquake in around 2000 or 2002.
Correct. And before that, there was Latur earthquake around 1993, perhaps. These two were very big earthquake in India. Fortunately, earthquake is uncommon in India. Fortunately. But earthquake is very common in Japan. Remember that. An earthquake is also very common in the western coast of USA, California, particularly California. Fine. Anyway, so you should know the history of earthquake. However, this is a benchmark. Whenever, this is not the only earthquake that has taken place in last 80 years. After this, there have been 500 or 1,000 earthquakes throughout the world. But this is a benchmark. Whenever an engineer wants to say something, he has to benchmark, he has to say against this particular earthquake. So this is a benchmark. But why we picked up 1940 earthquake as the benchmark earthquake? Because this is the first properly recorded earthquake. इसके पहले recording correct ढंग से नहीं हुआ करता था. So this is the first proper recording of earthquake in the world, 1940 El Centro. After that, in USA regularly, receives earthquake record hundreds and thousands per year. All of them are not important. But throughout the world, this was the first. Today, we have earthquake occurring at many places. Unfortunately, India has earthquake measurement system, but India had nothing in 1940. India started having it after the Latur earthquake. So now we have our own earthquake graphs also. So this is interesting, that pretty old, but this was the first properly measured earthquake graph. Second, although it is in USA and we are in India, engineers always talk about, in the background of this particular earthquake picture, just to compare a particular method. The problem of earthquake is, this earthquake even never repeated in USA itself. And obviously, this earthquake will never repeat in India. If in India, tomorrow an earthquake occurs, 100% guarantee that earthquake graph will be different. So finally, a student should ask me a question. If tomorrow's earthquake is going to be different, why we are looking at this earthquake which is 80 years old? It is useless. We will try to answer that. It is not useless. So earthquake on the face happens to be a big challenge to engineers. Engineers doesn't know where it will occur. how it will vary, how long it will remain. Engineers know nothing, but still there are few hidden things, hidden beauties that we will come to know what are the hidden beauties. If you look at the graph, even I am helpless, you are also helpless. You will say ग्राफ लेके मैं कुछ भी नहीं कर सकता, लेकिन हम करेंगे. Okay, so before I proceed to the mathematical beginning of today, any question, if you have any additional observation looking at the graph? So if I bring another 10 graphs of the world, you will see that each graph is all definitely much different compared to each other. However, a standard duration of earthquake is generally 30 to 40 seconds. But some earthquake, these are severe earthquakes. There can be short duration earthquake also, only 10-15 seconds also. But earthquake fortunately doesn't last for 4-5 minutes. Fortunately, let me tell you. Earthquake fortunately doesn't last for 4-5 minutes. Throughout the world, whatever earthquake graph we have taken, we see that it generally dies out 30 to 40 seconds. Now, this is the hidden similarity. The earthquake graph may be different from place to place, but how long it remains, there is a similarity, generally 30 to 40 seconds. No one knows why it is that much, but it is a fortunate thing. If earthquake remains for 4-5 minutes, the damage will be havoc. It doesn't. That is one thing. Of course, why exactly 30 to 40 seconds and not 4 to 5 minutes? Another branch of science is there who are doing research that is called geotechnical engineering. Okay, so it is their job, geophysics and geotechnical engineering. It is their job. They study why earthquake happens and why this kind of random graph is generated by earthquake. It is their study. Engineers don't try to dig into that. Engineers accept this graph. And then engineers faces the question, how can I design a building so that the building will not fail? How can I design something? Maybe a factory, maybe a bridge, a railway bridge over a river. The river should not fail. So engineers never question why the earthquake looks like this. It is not his job. Why the earthquake looks like this, that it is job of geotechnical engineers. Okay, a geophysicist. Engineers accept as it is, and then he sits down to design his component, which may be a high-rise building, which may be a railway bridge, it can be a chimney, like that. So how to design a civil structure for a probable earthquake, that is what we are going to discuss today, and it will take one more day. Okay, so to explain this, let me go to another slide. Let a minute. You be there. I have to change my slide.
There is a Richter scale. Richter scale.
Richter scale is the value of the earthquake, overall severity value of the earthquake. Richter scale, and that is a log scale. It explains or it represents the severity. Fine. But from Richter scale, engineers cannot do his design. Let me tell you. Suppose one earthquake is of 7 Richter scale. Another earthquake is also of 7 Richter scale. Your building may survive first earthquake, your building may not survive second earthquake. Both are of same Richter scale. So Richter scale is an overall earthquake severity. But engineers cannot use it. That okay, my building is designed against 7 Richter scale. No, engineers design in a different manner. We'll discuss that. Richter scale is an overall severity of earthquake. Okay, so that is based on energy. Not you engineers cannot design. So how engineers proceed to design? We start with this figure. So this is a single story building. This is a single story building. This
Sorry,
is
you
the
haven't said.
okay. Sorry. I haven't no, I haven't shared it, so you can't see it. Correct. Let me share it. So that is a problem. अरे आ जाओ picture में हाँ now you can see it. Okay, so you look at the picture. Now this is a building, single story building. These are columns. I have shown 2 columns. It doesn't mean that there will be 2 columns. These are for representation. Overall stiffness, they are in series. So overall stiffness K is the summation of all the columns. So this K represent overall stiffness. In the figure, there are 2 columns, but this building, there can be 4 columns, there can be 8 columns, doesn't matter. K is the overall lateral stiffness of the columns. So these columns provide lateral stiffness. Can anybody tell me how much is that lateral stiffness? Again, a difficult question, I know. If height of the column is h, okay, it is 12 EI by L HQ. Why it is 12? You have to find out from solid mechanics, or else you can refer the book Structural Dynamics by Maria Pijo. Okay, so that is in solid mechanics. Why the columns stiffness formula is 12 EI by L cube, H cube. Here length is for column, we say height of the column, H cube, 12 EI. Now, please remember this I matters. East to west, I may be some, if it is a square column, east to west, I may be same thing as north south I. But if it is not square, then east to west I will be different from north south I. So we have to be careful. So stiffness along east to west direction may not be same as stiffness along north south direction. Okay, that is one thing. Second thing is that although earthquake has 3 components, 2 horizontal, 1 vertical, our discussion will always be with respect to 1 horizontal component, which may be north-south, which may be east-west. So if we know how to do the analysis for north-south component, our mathematical procedure will remain same for east-west component. Only the earthquake graph will be different, but with that graph, whatever mathematical procedure we will do, that will not change north-south or east-west. So it doesn't matter whether this YT, which is the earthquake displacement caused by earthquake, whether it is north-south, whether it is east-west, we are not mentioning it, because whatever we can do for north-south, we will do the same thing for east-west. So it can be either north-south or it can be for east-west. Now, another thing that although I am saying earthquake is represented by YT, the strange thing is that Y as a function of T is not available with me. It is the acceleration as a function of time T which is available with me. The earthquake measurement instrument doesn't give me Y versus time T. It gives me Y double dot versus time T. It doesn't create a problem. We will see it now. So what is the equilibrium equation? Inertia force plus restoring stiffness force is equal to 0. Now this is a motion induced vibration. So the stiffness force will be difference of the displacement at top end and at the bottom end, because floor is also moving. So stiffness stiffness force will be K into X minus Y. And this is inertia force. We are neglecting damping now. We will bring damping later on. Right now we are neglecting damping. Now what we do is we take X minus Y is equal to Z. Then this equation becomes this, and which finally takes this shape. And now I think you have understood. So finally, this is the equation we try to solve. We don't try to solve this equation. We try to solve this equation. क्यों?
We are not aware with the values of x and y.
No, that is not the correct answer. What I'm trying to say, this equation is nothing but another form of my original equation. But I'm saying this equation we try to solve. We don't try to solve the original. Because here, my excitation, see what is this? This right hand side is excitation. It is excitation. It is a force. It is mass into acceleration. It is a force. And this excitation is available with me. My earthquake measurement, I have y double dot. So right hand side is known to me. That is one of the reasons. I could have written is mx double dot plus kx is equal to k into y. But y is not available with me. Whereas y double dot is available with me. So this equation engineers prefer, because right hand side y double dot is available with me, with him. Although this y double dot is not an analytic function. Be careful. This y double dot is never an analytic function. It is a random function, but it is available. It is available from that graph. Fine. Second reason why engineers prefer this is because during earthquake, if the building fails, matlab if the column breaks, then column will break because of large X, large Y, or large Z. Can you tell me?
So large Z.
Large Z.
Large Z. So here Z represents the damage, not X, not Y. X may be large, Y may be large. Still Z may be small and the building will not fail. Building will not fail. If X is large, the people who are residing, they will feel discomfort. But building will not fail. So that is the reason why in earthquake engineering, we always try to solve this equation. Okay? Is how to solve this, then we'll bring damping. Right now, we are neglecting damping. So how to solve it? We convert it into normalized equation. We divide by m. This becomes omega n squared minus y double dot. And now, what we do is, we apply Duhamel integral. So now this is tangent excitation. This is force, so we can call it Ft. So let us apply Duhamel integral. Do we get this? Tell me. Let us apply Duhamel integral formula on this formula. We have already applied Duhamel integral formula. Mx double dot plus kx is equal to f tau. उसके लिए हमारा Duhamel integral formula जो है, same formula if we use it. Do we get Zt in this integral form? That is my question. Carefully look at it. It's not easy. You take 2-3 minutes. अपना हाथों से एक बार लिख के देखो, ये फॉर्मूला ठीक है कि नीचे में एक m आना चाहिए, 1/m ओमेगा n आना चाहिए क्या?
No, sir. Only one equation is right, sir.
No, this is right because I have written it. This has to be right. But sometimes you get confusion. No? So I'm trying to remove that confusion. So this Duhamel integral now tells an engineer that we can carry out this integration. If we can carry out this integration, we get Z as a function of time t. ठीक है? But how to carry out this integration? I know y double dot, but it is not a so this
Yes,
integration
exactly.
is never carried on analytically for earthquake, because for earthquake I only know the values after every time gap. This time gap generally is very small. El Centro earthquake was measured with a time gap of 0.02 seconds. So if it is not analytical, how can I do the integration? Answer is simple. We can do the integration. Anybody who knows the trapezoidal rule, I'll pass on this. El Centro data set, which is roughly for 40 seconds, little less than 40 seconds. अगर 0.02 सेकेंड में डेटा लिया गया और 1600 के आसपास डेटा है, तो टोटल ड्यूरेशन कितना होगा? इतने में भी टाइम लगता है ना? El Centro data set is roughly 1600 and time gap is 0.02 seconds. So what was the duration of the earthquake?
32 seconds, sir.
32 seconds. Okay. So I will give that data. If you know, first you learn what is trapezoidal rule of integration, that is numerical integration. उसको MATLAB का प्रोग्राम लिखो. प्रोग्राम का इनपुट होगा the value of y double dot as an array. Tau is equal to 0, this was. Tau is equal to 0.02, this is the value. Tau is equal to 0.04, this is the value. So the values using which we have plotted the graph, that values as an array. It is with me, I can give you. But suppose values are available, can we carry out this integration using numeric? If you know trapezoidal rule, do you think you can write a program so that you will get z as a function of time t? And if you get z as a function of time t, you can draw the graph. You can draw the graph. And you will see what is interesting is you will see this z is also random, but not as much random as the earthquake itself. But it will also vary in a very abrupt manner. But can you plot this z? If I ask this question, let me see. आज हम डिस्कस नहीं करेंगे सॉल्यूशन. लेट मी फोकस ऑन earthquake only. What do you think that if you learn numerical integration trapezoidal rule, and if I give you this data for 40 seconds, 32 seconds, do you think you can carry on this integration and plot this graph in MATLAB? Either yes or no. Answer is yes or no.
Yes, sir.
किसने बोला?
Yes.
नहीं, नितेश बोल रहा यस. एक जगह फंस जाओगे. There is one more unknown that you don't know in this integration. What is that unknown?
Natural frequency.
Correct. So you can find out Z with an assumed value of natural frequency. ठीक है? तो you assume a value of natural frequency, then you can do the integration, you can plot the graph. Once you plot the graph, you can locate the maximum value Z max. ठीक है? Now you change your natural frequency. Again you do the integration. You will again get another variation of Z and another value of Z max. So if you do this, if you run this program for different value of omega n, every time it will get a different value of Z max. Agree? If that Z max you plot, you get this graph. ठीक है, इसको थोड़ा छोटा करते हैं तो ग्राफ नहीं दिखेगा. So this is omega n. And this is the maximum Z relative to base. So y-axis is Z max, x-axis is natural frequency. So if with El Centro data, if you write your program and you run the program for different values of omega n, you will get different values of Z max. And finally, this is how Z max will change for different natural frequency. Okay? So this is important, and this is called response spectrum. This graph where maximum displacement is plotted against, sometimes we plot it against natural frequency, sometimes we plot it against natural time period. Okay, frequency is related to time period. लेकिन time period में क्या होता है? High frequency means low time period. ये चेहरा time period में यहां से चालू होगा. Okay, that is the thing. Reverse है. Frequency अगर ज्यादा हो रहा, time period छोटा होते हैं. So this particular graph, x-axis is natural frequency, y-axis is relative displacement maximum value, and we get this graph. तो एक ग्राफ देख के अभी आप लोग मुझे बताओ, एज एन इंजीनियर, दिस ग्राफ इज टॉकिंग टू मी, हेल्पिंग मी टू मच. दिस इज $1 million graph to me. Why I am saying this graph is trying to help me?
According to me,
Louder.
according to this, we have to make a building such that natural frequency is higher, so that its maximum displacement will be less.
This graph, now this is an interesting thing. This is the graph we have generated for El Centro. And what we find, that if my building has a natural frequency outside this range, that is above 20 cycles per second, that is hertz. If I have designed a building whose natural frequency is greater than 20, what I will say? That if tomorrow another El Centro earthquake comes, my building is safe because resonance will not occur. Resonance will occur if my building has a natural frequency between 0 to 20. Now, having said this, immediately a question will be raised that tomorrow's earthquake may not be similar to El Centro earthquake. So what engineers have done, they have studied thousands of earthquakes in last 40-50 years, and they have found a beautiful hidden fact. This response spectrum, it stretches maximum up to 33 hertz. Maximum 33 hertz. So earthquake may be different. Richter scale may be different. Even how it varies, it may be different. But its spectrum duration is generally doesn't exceed 33 hertz. So this is a beautiful similarity engineers have noted. So if I can design my building beyond 33 hertz, it is 100% safe against any earthquake in future. However, having said this, still the problem remains. Engineers still faces a problem. That it is very easy to say that if I can design a high-rise building having its lowest natural frequency greater than 33 hertz, the problem is buildings cannot have its natural frequency as large as 33 hertz. बिल्डिंग का नेचुरल फ्रीक्वेंसी काफी कम होते हैं. क्यों कम होते हैं बिल्डिंग के नेचुरल फ्रीक्वेंसी? कैन यू एक्सप्लेन?
So because the mass is very huge.
Because the mass, that is the problem. All buildings made of this concrete, and that is why Japan has gone to wood. Now you can appreciate why we prefer wooden buildings. Reduce the mass. The moment we reduce the mass, we increase the natural frequency. So sometimes we add extra concrete material in the building. We make it heavy. As far as earthquake is concerned, the building becomes more dangerous. because it's natural frequency. So today in India, people don't bother because earthquake doesn't occur as frequently. But in USA, every building has to be designed against a possible earthquake. So he has to take a certificate. It is called ERD, Earthquake Resistant Design. So an ordinary contractor cannot build a house in US. He has to design his building against a possible earthquake because earthquake is very, very common. In India, only one construction requires design against earthquake. Can anybody guess it? I will take another 2 minutes. In India, only one design is done where possible earthquake occurrence is taken care during the design.
So dams.
Nuclear power plant design. And I was involved in half of nuclear power plant design 30 years back. The consultancy company I was working, they designed almost all the nuclear power plant of the country. Okay, so I know how it is designed, what is the pain. So nuclear power plant design has to take care of earthquake. The reason is simple. If a disaster occur in nuclear power plant, the damage is havoc. We know Chernobyl and then Japan earthquake 212 or 208. So in India also for nuclear power plant design, we consider possible earthquake. Thermal power plant, we should. Gradually a time will come when thermal power plant also need to be designed against earthquake. A time will come when these flyovers, bridges, they also should be designed. In India, it is not considered that important even now. So aaj itna hi, and I will pass on these 2-3 pages, the derivation, all this derivation in presence of damping, I will pass it on to you. So next class, we will again have some discussion on earthquake, and that will be the last class of transient excitation. Okay? Tomorrow, I will not engage the class. We will meet again possibly on Tuesday. Okay? Chalo, ho gaya. I'll give you the graph up to this. We have discussed a very important practical subject today, earthquake and how it is taken care of by engineers. Chalo, you can leave.